Alright, we've made it all the way to pre-calculus, and the last couple videos, trigonometry, I'm still kind of getting the hang of it, still studying it. There's so many topics to comprehend, and it just seems like an endless subject. Reading about algebra, there are just endless textbooks and documents about geometry, trig. There's just so much to catch up on. So I haven't been able to really wrap my head around all of this, but I'm trying to push through this series. I haven't uploaded any videos over the last 3 months because I've just been getting so deep into the sauce of these mathematical topics, and a lot of Dunning-Kruger coming over me, a lot of self-doubt, not really understanding what I'm learning. But here we are, we're in pre-calculus, and pre-calculus is kind of just summarizing all of the topics. Our main topics have been functions and their properties, polynomials, exponentials, logarithms, trigonometry, sequences and series, vectors, parametric equations, and this stuff we've already kind of gone through in previous videos. But I came across a pre-calculus textbook, and there was a couple other topics that I haven't touched on yet, so we're gonna quickly brush on these topics before we get into the next video, which is going to be the actual calculus video. So before we get into calculus, we got a few more concepts to really brush on, and I'm going to be making a little return to the trigonometry video. We're going to be working on that half angle and the double angle equations, which I skipped out on the last video because it was just a lot. I wasn't comprehending it, but we're coming back. So the main topics of this one is going to be parabolas, hyperbolas, ellipses, limits, and behaviors, imaginary units, and of course just wrapping up that trigonometry. So let's get right into this. I appreciate you guys for being with me. We're starting off with parabolas, which are called conic sections, and this is kind of understanding the vertex form and the standard form of a parabola. So a parabola is a U-shaped curve that can be upwards or downwards or sideways. You could be driving on a street, take a U-turn. You're taking a parabola, right? If I type in a U, that's a parabola right there. So here we're going to essentially map out this parabola. So we're going to import number pi as np, and we're going to import matplotlib. And I'm going to enter this, let's spin up this virtual environment here. First, I'm going to import my numpy as np. If you're going to be importing this, you can see as I just ran, I just finished downloading it, installing it again. So to install it, you just do pip install numpy. Before you hit enter on this, you want to click on here at the bottom right hand corner of the screen where it says Python, right by your system tray. Click on this. Here it brings up the .venv, which is the recommended environment. If you don't have this as an option, then you're going to want to do a command that is python -m venv space venv, and hit enter on that. Once you hit enter on that, click on this little thing again, click up here, and that should be ready to go. So I'm also going to import matplotlib, the pyplot library as plot. So, and again this one, so we'll do pip install, and now that's ready to go as well. So if I hit play on this to run it, I get no errors, so everything's installed, looking good. And I'll go ahead and create that first plot function to plot my parabolas. And so here we're trying to plot the form of a parabola to go vertically and horizontally. So with the U, you have the horizontal, which is the little line at the bottom that's connecting the two vertical lines of the U that's going up and down. So in this case, the vertical of a U the U vertical lines, these are like y equals a. So like this is like a formula to calculate the line. So this is just kind of like a formula I found in a textbook. And then we've got the U horizontal line. That's going to be x, which is a. And now these are just kind of like the formula equation that I found out of the textbook. So it's like x equals a, and we'll fill in the blank of what all these are. So the first thing, we got the a that's sitting here, right? First of all, we got the y. So y is our vertical line, x is our horizontal line. The a is gonna be what's called the coefficient, and that controls the width and the direction of the parabola. So that's width and direction. Then next we got the h, this one right here. So the h is the x coordinate of the vertex, which is going to be this one. And then the k is going to be the y coordinate of the vertex. And then the x range is going to be the tuple for the range of x values. And then we have, so basically in here we're going to fill this out. So this function is going to take an a, h, k, and our x range, which by default we can set it. So by default we can put -10 and 10. And then we could put in our parabola type, which could be vertical, or we could set it to horizontal. But so here we can put in our x values, and we'll take a numpy linear space or x range. So we're going to give it a range of 0 to 1 to calculate with 400. And if the parabola type equals vertical, then we're going to do the equation that we mentioned up here. So that we're gonna perform this equation here. So we're gonna do y values equals a times x values minus h exponentiated by 2 plus k. And then the plot, we can put on the x values by the y values by the label of the parabola, and this is going to be our label right here on the plot chart. So this is just kind of like showing the equation. And our plot x label, we can mark this as x, and our plot y label is of course going to be a y. So then the next statement, if it's not a vertical, if the parabola type is actually just a horizontal, then we will go ahead and do our horizontal equation here with the same linear space, with the same range. I'm going to use the same range and calculate our x value minus k. Same thing to the power of 2 plus h. And we're going to plot this out and then just type out what we want to see on the graph itself. Yeah, this is supposed to be a k. So put the k goes here. The k is the y coordinate, the h is the x coordinate. And of course, the else, you know, if we didn't get a vertical or a horizontal, we got something completely irrelevant like a grapefruit. Invalid type. Must be vertical or horizontal. And then we're gonna pretty much plot our vertex right now. So we're gonna do plot scatter. We're gonna put in our colors. We can put in our orders. and our label. Pass in our X and Y coordinates here. And now we're going to put in our horizontal and vertical lines like so. And I'll make them both black. And the line width, I'll make them both 0.5. And I do want this to be a grid, so I'll put that as true. And I am going to add a title, parabola type, parabola, just like that. And then of course we want to show it, to plot show. And then here we're going to kind of use it. So we're going to do an A and our H and our K. So back here, the A is the coefficient, the width, and the direction. So this is going to control the direction and the width. H is going to control the X coordinate, and K is going to control the Y coordinate. So if I could do 1, 2, let's say 3, I could plot this with my AHK with the X range equals minus 10, 10. Parabola type, let's say vertical. If I hit enter on this, alright, so here's our U-shaped line right here. And if I were to reverse these numbers and play this again, what if we do like 35, 21, and 11? So now we get a different kind of graph. If we do 5, 4, 2, then what if we do, let's do 3, 1, 3. So now we got like a deeper curve here. And so I'm just gonna push this to my GitHub here. It'll be the link in the description below. So next we get to move on to hyperbolas, and I'm just gonna copy paste our parabolas over here. And I'm just gonna change a couple things around, right? So instead of doing plot parabola, I'm just gonna do hyperbola, and we're gonna have the same, pretty much the same ones. I'm just gonna replace the H. I'm gonna add in one more. I'm gonna do a B. So we got one more kind of angle to this, and instead of doing parabola type, we're gonna do hyperbola type, and we're gonna focus on the horizontal on this one. So for the hyperbola plotting, these are kind of our, we got a horizontal as well, you got a vertical. So with this, our horizontal equation is going to look kind of like this. So we'll have an x value minus a h value to the power of 2 divided by a value to the power of 2 minus y minus k to the power of 2 divided by b to the power of 2 equals 1. I guess that's what it shows in the textbook. I don't really understand what the 1 is for. But here we got y minus k to the power of 2 divided by b to the power of 2 minus x minus h to the power of 2 divided by a to the power of 2 equals 1. So over here, we're going to redefine these values. Actually, our x range is going to be the same, so we can leave that. Our k is the same, and our h values are the same, so we can leave those two. These are more focused on the parabola, so I'm going to delete this. So now we have our a and our b. So with hyperbolas, the a was our coefficient, which was the width and the direction. So here I'm going to do, a is actually going to be this is our horizontal width. and b is our vertical width. And going down to the x values, we can leave this actually exactly the same. And for our parabola type, I'm going to put in hyperbola type, and we'll set this to horizontal. And now this part is going to be completely different, so I'm going to delete that. And we're going to bring back our equation. So this is our horizontal, right? So I'm going to grab this equation right here, slap it there, and this is the one we're going to work with. So we get our y values positive, positive y value, and then we have our negative y value. I can give this better names. So we get our positive y value and our negative y value. So it's going to be, these are pretty similar. So I'm just going to type them both out at the same time and just edit the couple differences afterwards. So we got our x values, take away h to the power of 2, divided by a to the power of 2, take away 1. And then here on this end, we're just going to flip this. If we want to flip a positive to a negative, we're just going to flip this to a subtract. And I think that's it. And then with the map plot, we're just going to label it. We're just going to validate whether it's positive or not. Yeah, we'll just go on to the Ellipse. So here we're gonna, if the type was vertical, then we're gonna put in this equation right up here, which is pretty similar. And I'm just gonna copy paste these two lines. These are gonna be our x values. And instead of using the k, we're gonna do h plus a, and h minus a, like that. And then we'll do an else statement. Arrays, value error, invalid type, choose horizontal or vertical. And then down here, so we've got another letter to add in. We've got our b value. So we can do 3, 2. So this is going to control the horizontal distance from the center. This is going to control the vertical distance from the center. This is the coordinate of the center. And this is the y coordinate. So this is the x coordinate. This is the y coordinate. Error here on line 41. Alright, so here's our coordinates here. So if I were to go like minus 0.4, let's do like a minus 0.04. And here I'll do 4 minus 0.05. So you can see here on the y-axis it says 0.05. Here on the x-axis it's a 0.04. And here is the distance. This is the vertical distance from here. And this is the vertical distance here, or the horizontal distance from the center, which is here. So next we're moving on to ellipses, which is again pretty similar. So I'm gonna copy paste this whole script over to ellipses. And here we're gonna use the A, the B, H, K. We're not gonna have a range though. Instead, ellipses is more about the angle. So we're gonna set an angle at 0 for now. And we're going to add in a number point system. We'll put it at 400, which is what we've been using down here. And we can actually delete this line now for the x values. There's going to be a couple different things here. So the ellipse plotting, the equation is going to be a value of x minus h to the power of 2 divided by a to the power of 2 plus y take away k to the power of 2 divided by b to the power of 2 equals 1. So to break these all down, once again, I'm going to leave H and K exactly as is, and actually A and B are also exactly the same here as they would be in the hyperbolas. So here we just have a couple of weird things. We got the angle and these number points, right? So what are these all about? So the first one, we're going to talk about the angle. The angle is going to be the rotation of the ellipse in degrees. And 0 equals no rotation. The next one is our number points. And these are used to plot the ellipse. And the default that we set is just 400. And that's just kind of a plot number that's recommended to use with matplotlib when I was reading about this equation. And this one, we're actually not going to be using any if-else statements like this. I'm actually going to update the name here. Ellipse. We're not going to use an if-else statement. This is all just going to be plotting. So first one is going to be our parametric equations for the ellipse. So we got t equals, we're going to take the linear space of the numpy library, do 0, 2 times n times pi times our number points. And then we're going to do our x value, which is going to be a times np. We're going to take the angle of the cosine and pass in our t variable here. Then we're going to grab our y value, where we're going to calculate the sine angle. And we're going to create a rotation matrix. So we'll do an angle of, we're going to grab our radian of the angle. So we're going to grab the radians of the angle that we provide. And we got our x rotated value. So if we rotate the value, we're going to get x times the cosine. We're going to times the angle radians minus y times np sine times the angle radian. And we're going to grab our y rotated, which is pretty similar to the equation above. The only thing that's going to be different is we're changing the cosine to the sine because we're just calculating the different angle. And we're going to flip the minus to the plus because it's the opposite angle. And change this to the opposite angle as well, to the cosine from the sine. For the ellipse, we do have to then, so we've got the scatter and we can plot it. The lines are good, the grid is good. The title, we can go ahead and call it ellipse. We're going to plot the y label. And here we can set the angle. So let's say we got 90-degree angle or something like that. And then we go plot ellipse. BHK angle is going to be angle. So coming back up here, let's see what we got going. So we got our y, our x. We could add a few more things onto here. Like maybe we can shift it. So we could do an x shift equals, it's going to be our x rotated plus h. And then we're going to do a y shift. So we're just shifting our y over maybe. And then we can go ahead and plot it. So we get x shift, y shift, and add in our labels here. And we can just pass in some of our values. Okay, here you go. Yeah, now we get a circle around the dot. So that's pretty cool. But yeah, that's what I was trying to do. I was trying to get that circle in there. So, yeah, and if we change the angle to, let's say, like 45, yeah, so you get kind of a different kind of angle. So that's cool. It's kind of like a galaxy, like the Milky Way, if you want to imagine that, if you have a crazy imagination like mine. But, yeah, so That's a pretty cool one. So with the limits, we're going to be playing around with, there's a concept called limiting when it comes to computing and plotting out and creating functions, creating limits on things. So we're going to be using the numpy as np. We're going to use matplot library again. And I'm going to be using the SIMP module for the first time. And I believe this is for symbolic links, like the symbolic Python module. And since I've never used this, I gotta install this as well. Pip install SIMP. And I've just been reading through this forum with the example uses of SIMP. I went through this random, I guess not random, this is the actual SIMP self-created documentation, about how you can use these limits. It's good for derivatives, integrals, and series expansions. I don't know what series expansions are yet. I think that's one thing we haven't really covered. But so here it's kind of going over all the different limitations and ways that you can use the limit functions to create your own limitations or keep track of, to evaluate a limit at one side only, or two sides, or three sides, or whatever you're working on with. So speaking on that example of putting the limit to one side only, that is one thing that we can start with creating a function. So we can define a compute limit. We can put in our function, our variable, our point, our direction, and our direction can be, I don't know yet, but essentially, let's define these. So we have function, right? A function is like, a function is what we're using right here, right? Like define function, the stuff that we've been doing this whole time. So you can, that's one of the things. A variable is, a equals 2. It's where the limit is being taken from. So you can assign a 2 to a. And then a point is going to be the point at which the limit is computed. So it's kind of like the threshold, I guess you can call it. That's when the limit is computed, is processed, I guess you can say. The direction is going to be the direction of the limit. Is it, back at the example, it says limit at one side. Is it the left side or the right side? Or is it both? So that's like what the direction means. Is it left or right? One side, both? And so here we can go in and put in our if-else statement on this, right? So if I remove this, what do you think our if-else statement is going to have? We're going to have three options, right? Three options and an error block. So we're going to have if direction equals, we'll start with both. And then we're going to do else or elif direction equals left. Right, and the next one's going to be direction equals right. And our else is going to be our error catch block for our value error. Going to be invalid, right? So our if it's both, we're going to return our SP limit, and our SP is our SIMP. So we're going to return the limit of the function times the variable times the point. And if it's left, we're going to return the SP limit times the function times the variable times the point and times the direction, which will be a subtract sign. And then we'll do return SP limit if it's a right on function, variable, point, and the direction is going to be a addition sign here. And then next we can go ahead and plot the function. So we're going to plot the function near the limiting point. So def plot function. So we're going to plot out the function. A couple other new words I've been learning is the function expression. We're going to add another variable, another point. We're going to add in an x range, similar to how we're doing the parabolas. So we're putting our default with the -10, 10, just because that looked pretty good on the matplot library in the last examples. We'll do limit value. We will have no limit value for now. So talk about these. We got the func expression. The function expression. This is the simpy expression of the function that we're creating. So this library here is going to have its own expression on our functions. And then again, the variable is the same as up above. The point is the same as up above. And then the x range is the same as the x range we used back here in this example. So, you know, to keep it on point, I'm just going to copy this over here. It's the same thing. And then we have our limit value. Our limit value is the value of the limit, if known. And if it is known, it'll display it on the plot. And we're gonna bring in this function called lambdify, which is a brand new function. I've heard of Lambda in AWS, which is like a serverless function, but I've never actually heard of this before in Python. So lambdify is, I'm gonna be honest, I don't really know what this is, but from what I'm getting from this is that this converts a simpy function to a numpy function. Because up here you see we have the numpy library, and then we have the simpy library, and we have the matplot library. And the matplot library, it plots stuff from numpy libraries really easily, and some stuff from simpy libraries, like simpy functions, aren't as easily plotted. So we have to use this lambdify, which pretty much like converts a simpy function to a numpy function so that matplotlib has an easier time to work with it. Okay, so we're gonna name this function convert simpy to numpy. All right, so it's gonna do simpy lambdify variable function expression, and we're gonna just put in the string for numpy. So this is our convert simpy function to numpy function for matplotlib readability. And the next thing we're going to do is generate our x values. So we're going to do the x value, put in our linear space within our x range. And this is kind of the same kind of x range that we created. You know, we can go back to the hyperbolas, grab this, same thing. You know, this is our same x value that we created here. We're just going to stick it here. It's just a common one that's often used in these examples to generate x values. And we can add to that by excluding the point of discontinuity, like excluding the limiting point to avoid division. Like, you know, whenever there's like a 0 and you have issues dividing it by 0, then we can add in we could add in something here to avoid that, but I haven't really, yes. So there could be a bug in here if we were to divide something by 0. And I could add in a line here to prevent that. I don't really know what line to put in right now. But we're just going to continue. So it doesn't matter if there's bugs right now, because this isn't like anything that anyone's ever going to use. This is just like my own studying. But anyways, so we got the plot function for the y values. Our y values are not the plot. what is our y? The y values are going to be generated using the lambdafied function. Okay, so we're going to grab this and we're going to multiply that by our x values. And then we're going to plot the function and we're going to pass in our x values, our y values, our label, and we could pass in our mark. We can mark the limit point. So we do plot ax on the vertical line. Our color can be red, make it stick out. The line style, put in the label. Actually, line style, we could do like two couple squigglies here. So earlier I had the limit value at none, so I'm going to put in if limit value is not none. Then I'm just going to put in all the generic plot lines that I normally put in. My horizontal line, my vertical line, my labels, and the title. We're going to put in a SP symbol, and we can define the function. So we'll do x to the power of 2, take away 1, divided by x take away. Then we're going to do limit at, I don't know, like 5. So compute limit function x 5. We're going to do print limit of the function as x minus greater than 5. And we'll do limit at 5 right here. Well, you know what? It is because I just never passed anything in here. I said I was gonna, yeah. So if I type in both here, right now it calculates. If I do left, I messed up by my own script. And if I do right, okay. And then, yeah, so now I can plot the function as well. Put in the function x, pass in our x range value. Could put in like, I don't know, like -5 to 10. And put in our limit value for our limit at 5. Yeah, right there. And then, if I hit play on this, oh, the squiggly line is not valid. So I gotta come back up here, and I gotta change the line style to, we could do double dash like that. So we can see that vertical line right here. It goes all the way down at the middle. It's red. We can see that. Here is our green point right here. So you can see that. See, it's like we can see our angle. Our angle is going up all the way to 10. But we set our limit right here. And this is where it limits it. So going over to the end behavior, which is kind of another similar concept to limits, which is why I'm just going to copy paste what we got in limits over to end behavior. So this kind of computes the end behavior of a function symbolically as kind of as like a x value would approach infinity or negative infinity. So it's going to have the same function and it's going to have a variable. So I'm just going to delete this main part here. I'm going to delete it all the way up to here. Yeah, I'll delete it all the way up to here for now. Because we're going to want this plot stuff. We can delete this. Okay, everything's still going to be plotted out. And we're going to define and behavior. We're going to pass in our function and our variable, which is going to be exactly the same as right here. And we're going to do a limit at positive, and we're going to do a limit at negative. So we're going to be using that simpy limit library with our function, our variable, and our so over here there's like a little infinity sign, and that is just 2 lowercase o's. So if I'm coming back here, I'm setting the limit to infinity. Alright, I'm going to set the negative limit also to minus so this is negative SP infinity. And I'm going to return limit at positive and limit at negative. So I'm gonna make sure to return that, and then, so this is defining or computing the end behavior symbolically to infinity, right? And this is gonna be function to plot and visualize end behavior. So we're gonna define this plot end behavior. We're gonna pass in our function expression, our variable, our x range, which we'll put a default to -10 to 10 as our range. And going back, we're gonna grab function expression and x range. So these are two reoccurring things. So we got the function expression, which we had in the limit script. The x range we've had in multiple scripts so far, and it's using the variable, which is defined up here. It's the same type of thing. And basically we want to convert this again, and we want to generate our x value, and we want to generate our y value. So we're just going to grab this whole thing, put it right back here, and so we've converted the simpy to numpy with lambdify. We've generated the x values with the linear space from numpy, and we've taken the y values with the conversion passed in with the x values, which is using the numpy library, and we've got our plot gridded out, or plotted out I mean. So from here, all we have to do is plot our function. So we're going to do plot the x values by the y values, add in our label, which is our function. We're going to do the simpy with the pretty module to make it look pretty, with our function expression, which is this right here, which we're lambdifying. And then down here, all we have to do to use this is do x equals sp symbols. We're going to use an x again. We're going to define the function, which is, we can do 3 to the power of times 3, take away 2, times x plus 1 divided by x take away 1. And then we can compute the end behavior as x approaches infinity and negative infinity. So this is what we're going to do, print end behavior as x infinity and beyond. Here I'll type in limit at negative, and right above this I guess I will call these functions as well. And then we can plot the function and visualize. So we can do plot end behavior. You know what, this is actually just end behavior here. So this one, we're not plotting this one. Okay, so we've got the end behaviors here, but we don't have the plot because I actually have to pass in the parameters to actually get the plot up it. Let's hit play on this. And here it is. So here's our little blip right here. That's where we're getting the our limits. And coming to these last 3 topics, I still need some review on these further. So I'm gonna have to cut this video here, and we'll do a part 2. Thank you for watching, guys.